Hello, we're going to be going over Chapter 10 for the Top Hat textbook. This is the second edition. In this one, we're going to be talking about adding molecules onto a carbon-carbon double bond. So Chapter 7 and 8 were about making carbon-carbon double bonds. This one, we're going to be doing chemistry to them. Okay? And so for a lot of these, what we're going to be doing is we're going to be taking the double bond and adding things across it. So one half the molecule goes on one side, the other half goes on the other. So we're going to be adding, say, HX, and so remember, X is typically going to be a type of halide, so chlorine, bromine, iodine. Chlorine gets a little weird sometimes, but that we can also add water across that. And that one, we just have to think of water not as H2O, but as HOH. So an H goes on one side and an OH goes on the other. We can also add just the halides themselves. So, Cl2, Br2, I2. And so where an iodine goes on one side and the iodine goes on the other. But a lot of these are going to use a very similar mechanism. So the way this is going to work is the fact that you have to remember that the carbon-carbon double bond is nucleophilic, right? You're putting 4 electrons in here between those two carbon-carbon bonds, okay? And so that is going to have negative character to it. That is then going to be attracted to the polar covalent bond of, say, the XH. And so as we form this bond, okay, these two electrons here in one of these pi bonds is going to want to make a bond to that hydrogen. Okay, so that bond is going to go here. The 2 electrons that are here, right, those are going to go up onto the halide, right? Because hydrogen can only have one bond, so it's got to get rid of those, and so those become a new set of lone pairs here. Okay, and since the hydrogen can only go on one side, that means the other carbon is going to only have 3 bonds. And so if you go in and calculate the formal charge, it's going to have a +1 charge. So you got something negative, you got something positive, and so the halide here is going to be attracted and want to form a bond with that positive charge. And so essentially what you've done is you've taken a carbon-carbon double bond and added H on one side and a halide on the other. Now, the order of activity, as it turns out, is HI is actually going to be a lot more reactive than HF. Okay? So that is the relative order of reactivity. But if you notice, so we could get the H here, right, and the Br here, or to get this product, right? Or we could have added, right, the H on this side and the Br on this side, right? And that would have resulted in this one. So the question is, how do we know, do we get both? And if so, do we get equal amounts of it? It turns out that we can actually predict which of these 2 possible ways, right? Is it going to go like this, or is it going to add like that? We can predict that. Okay? And it turns out Markovnikov discovered the preference, okay? And it all has to do with the stability of the carbocation intermediate. Okay, so what's going to happen is the halide is going to go on the more substituted side. Okay, so you're going to look at the 2 carbons of the carbon-carbon double bond. Okay, and so if you look at this one here, right, how many carbons are directly attached to that carbon? Well, there's just 1, so that's primary. For here, for the other side of the carbon-carbon double bond, right, it has 2 carbons directly attached to it, this one and that one. And so that's secondary. And so what ends up happening is this is the more substituted side of the alkene, right? It has the fewer the fewer hydrogens on it. Okay, and so Markovnikov says, look, we want to the bromine is going to want to go on that side, because if we come in here and we do this, right, this is going to attack here, push that there. We have two possibilities. Okay, so this is where the alkene originally was. So if we put it on this carbon here, or if the hydrogen goes here on this middle carbon, then what we're left with is a primary carbocation, and that's really unstable. So there's just not going to be a whole lot of this around. Okay, what it would rather do is it'd rather add the hydrogen here. Right, so the hydrogen ended up going on this side up here. This side it ended up going here. So the resulting carbocation would be secondary, and so this is going to be a lot more abundant because it's a lot more stable. And so when the bromine comes back to attack it, okay, this is pretty much all it's going to see. And so this is going to be the major product. So again, this is where the alkene originally was. Right? This side is primary, this side is secondary. Notice how the Br, the H, which goes on the lower side, and the halide goes on the higher side. And again, it all has to do with maximizing that carbocation. Okay, so if we can get the carbocation to be a, say tertiary, if it has a choice between a secondary and a tertiary, right, it's going to want to put that carbocation on the tertiary carbon. Okay, and so that's where the bromine would ultimately go. So here it's, we're talking about, primary versus tertiary. Well, it's definitely going to want to have that carbocation on a tertiary carbon. So that's where the bromine ends up. Now we would talk about this because this issue of syn versus anti. Okay? About that. So if because a lot of these reactions are going to produce products that are going to get added either one way or the other. Okay, so if the two groups that get added to the alkene are on the same, end up getting added on the same side. Okay, we call that syn addition. Okay, they could either be both up or both down. Doesn't really matter. If you've got 180 degrees, right, one up, one down, then that's an anti-addition product. And so for a lot of these, for some of these, you can go ahead. We could figure out if it's syn or anti by the mechanism. Okay, but that's not always the case. Okay, so sometimes you just have to memorize it, unfortunately. So for this one, when we're adding HX, okay, so whenever you go through this carbocation intermediate, remember it flattens out. Okay, and so what can happen is, so after you form the carbocation, that flattens out, and so half the time it comes from the top and half the time it comes from the bottom. And so if this is what's called a prochiral center, yes, the bromine gets added on this carbon here, but you can actually make different enantiomers. You would make both enantiomers for this. So again, this can get a little complicated with this. Now the question is, so we can, if we had this molecule here, and we wanted to put the bromine on the more substituted side, right? So this is tertiary versus primary, right? No problem. We just put an HX. But what if we needed to switch that? What if we needed the bromine here, right? What if we needed that bromine here on the primary side, on the lower ordered side? Well, you'll see this a lot in chemistry where we do it one way and then we try to do it another. Right? You have one preference and then you try to do the other preference. Well, it turns out what we have to do is we have to actually swap out and do a different mechanism. And what's required is some sort of peroxide. Okay, the peroxide actually gives the anti-Markovnikov product, right? Because look at this, right? This is tertiary, this is primary. Same thing down here. So if there's no peroxide around, right, then the halide's going to go on the higher ordered side. If there is peroxide around, okay, then we're going to go on the lower ordered side. Okay. And so you have to look at all of the reagents that are in there that are getting added. Okay. So if we're looking at this, okay, well, how we want to take a look at this is to say, okay, what functional group are we looking at? Okay. We have ourselves an alkene here. So what's the reagent? Okay, so this is the reagent. Thing that does the transformation. Okay, so alkene plus HCl, right? What we're going to be doing is this, we're going to be adding H on one side and Cl on the other. Okay, so that's how you have to think about this. This sort of the decision tree. Okay, so I've got an alkene, right? What is getting added to it? Okay, well, we're adding HCl. How does that change the alkene? Well, we add H on one side and Cl on the other. Is there peroxide around? Turns out no. So that means it's just a regular old alkene. Okay, and so what we're going to be looking at, let me do this in a different color. Right. We'll be looking at these two carbons, right? So this one here is tertiary, right? Because there's 1, 2, 3 carbons attached. This one here is secondary. Because there's 1, 2 carbons attached. Okay? And so we could get either product. But this one's going to be the major. Because here the bromine is on a tertiary carbon. So it is going to be the major product. Now for the bottom one, we have several functional groups, right? So this is a ketone, right? This is an ether, and this is an alkene. Well, we don't know any chemistry to deal with ketones or ethers yet, so we're just going to focus on the alkene for right now. Okay, so again, we're going to be, so what's the reagent? Well, it is HBr plus peroxide. Now, it is going to change that alkene. We're going to be adding HBr across it. However, that preference is going to be switched. Okay, so now we're looking at secondary versus primary, and since we did add a little peroxide. Okay, now the bromine is going to want to go on the primary side, and so the molecule is going to look like this. We're going to add Br on the lower ordered side and the hydrogen on the other. Okay. Now, another way that we can do this, okay, so another version of this is instead of adding HBr or HCl or HI, that we can add HOH. Okay, and it turns out that we can do this, and it'll follow the exact same rules, right? So H on one side and OH on the other, and with Markovnikov, we're going to say, okay, that OH is going to go on the higher ordered side, okay, just like HBr. Okay, now with this one though, we need to add. We can't just put in water. Okay, technically we could, but we'd have to wait forever. We have to put in a little bit of acid catalyst to get this to go. Okay. And so the way this works is a general rule of thumb for a lot of the reactions that we're going to be dealing with in this book is the general rule of thumb is the catalyst is involved in the first step. Okay, it always seems to be that way. And then the last step is generally regenerating that catalyst, right? Because the catalyst isn't going to get used up. So even though it reacts, we at the end we have to spit the catalyst back out, so it can start the cycle again. Okay? And so remember, in water, right? It's H3O, right? So the water is going to grab a hold of that the H plus. But again, we've got something positive. We have a polar covalent bond, right? So even though the O is positively charged, it is a polar covalent bond. We have this polar covalent bond here, and so we are going to actually attack the catalyst first, the H plus. Okay, and that is going to kick away the water. Now, this is no different than what we were doing with HBr. Okay, we add an H first, leaving behind a carbocation. Now, we have carbocation. Now this is not negatively charged, but it does have lone pairs, right? So this lone pair is going to come in and attack the carbocation to add to make a new bond with the carbocation. This is no different than doing HBr. So we've added this. So instead of Br, we're adding a water molecule. Now the problem is, right, this isn't particularly stable, right? But if another water were to come by and snatch this hydrogen away, not only is it going to give it the correct lone pair, number of lone pairs on this to make the alcohol, but also you regenerate your catalyst. And that comes back down here. But we're essentially doing the same thing that we were doing before, right? You add the H, you essentially add an H plus to it, to the molecule, to the alkene, and then the other half comes in, right? In this case, it's a water molecule. Instead of a Br minus, it's a water molecule. And then you have to do some cleanup at the end. Now the problem is, with this reaction, is that we have a defined intermediate, okay, our carbocation intermediate. It's going to suffer the same problems we had with SN1 and E1 reactions, where you can get rearrangements. We can shift those carbocations around in order to be able to get to the to a more stable intermediate. And so what can happen is, right? So I'm just going to say this is H plus. Okay? And so if that happens, right, you draw in the hydrogens here. Right, we add the H here from the catalyst. Okay, that's going to leave a carbocation behind. Then what can happen is, if this methyl group here can then shift over, and so what we would be left with is right, because remember, these are all methyl groups here. And you're going from, so what you're doing is you're going from a secondary carbocation to a tertiary. So we'll shift it over just like it would happen in an SN1 or an E1 type of reaction. And it's at that point that the water molecule can come in and attach here to give you And then probably another water molecule will come in, and or something will come in to regenerate your catalyst. So that'll grab this there, and so you're back to that. So you remake your alcohol. If you want to avoid this, okay, so this totally fine, right? Follows Markovnikov, no problem. But you have to worry about these rearrangements. If you want to get away from that, you have to use different chemistry. In this case, it's what's called oxymercuration. Okay, and so what ends up happening is you have your alkene here, and you have this mercury compound. Okay, now the 1 and 2, what that means is we let the molecule react for a while with this set of reagents. We don't isolate the intermediate, but then after a while we then add this to it. So that's what they want. It's a stepwise addition. You got to do this for a bit, and then you got to do this for a bit. Okay? So so for this alkene, okay, what we're going to do is we're going to add HOH, just like the acid catalyzed hydration. It's no different. However, you know, it's going to follow Markovnikov, right? So we've got secondary versus primary, right? And so the OH is going to go on the higher ordered side, and the H is going to go on the lower ordered side. No problem. But there's no possibility for rearrangement. Okay, and so if you do this, if you try to add water across this alkene, okay, you've got this nice big tertiary carbon over here. You're going to get rearrangement. Okay, so eventually you're going to get, you know, after this, you know, the first H pluses get added, you're going to get a carbocation here, and then it's going to get it's going to shift over here. Okay, the hydride is going to shift, leaving the carbocation here. That's not a possibility with the mercury. And so depending on which product you want, you can do different chemistry, but this one is not going to do the rearrangement. The mechanism is, you don't need to, for me, you don't need to know the mechanism, but it does come down. The mercury sits on top of the on the alkene, and so there's going to be a partial positive charge on these things. But this is, again, this is the more stable of the two carbocations, and so this is going to be the one that's has a larger positive charge to it. So that's where the water molecule is going to come in. So you're going to get water adding on one side and mercury. You're eventually going to get mercury on the other. That's where the sodium borohydride comes in. One of these borohydrides comes in and displaces the mercury, and so you're left with this. But because this mercury is stabilizing both of these carbocations, there's not a possibility for rearrangement. Okay? But it follows the same rules. Now there are issues, right? Because you are doing mercury, so you're not going to want to do this on, you know, multi-ton scale. But for a small scale, it's okay. So for here, right, you've got what's your functional group, right? It's an alkene. Right? What's your reagent? Well, important one is this mercury. What does this do to an alkene? Well, in terms of an alkene, we're going to add HOH across it. Right? And we're going to follow Markovnikov, right? So we need to look, right? So this is secondary, this is primary. And so for Markovnikov says, the OH is going to go on the higher ordered side. Okay, so we're going to add. Right, so the OH is going to add here, and the H is going to add here. OH and H. That's it. So you draw it either way. Now again, what if we want to switch that preference, right? So with this, we can just like with the HBr, we can switch the preference on where the OH is going to go, and that's done through hydroboration. Okay, and so for here we use BH3. Okay, and it still leads to HOH. However, this HOH across the alkene, but this time it goes on the what's called the anti-Markovnikov product. The OH is going to go on the lower ordered side. Okay, so for here, right? So this is primary, right? That's secondary, right? The OH is going on the other side. So this was actually literally Nobel Prize winning stuff. This was discovered by Herbert C. Brown at Purdue. He was still alive when I was there, and I met him. Stuff like that. So interesting fellow. Let's put it that way. Now, one of the things is this is where the syn and anti comes into play. Okay, so it turns out that the H and the OH actually get added onto the same side. It's not usually a big deal if it's a regular alkane, but for cyclic alkanes, because you don't have that free rotation, it makes makes a difference, right? So in this case, the H and the OH are either both going to get added as dashes, or they're both going to get added as wedges. Okay. And so that can be important for your synthesis to be able to take that into account. Now, the way this works is the boron adds to the least substituted side, and it's just a pure sterics thing, right? So the hydride is really small, and so as it gets added, it can wiggle its way into this higher ordered side because it's just smaller. Okay, so that leaves the BH2 to go onto the other side. Okay, and so here's the H that we're going to be added, and the peroxide comes in and replaces this, oxidizes up the boron to leave behind an OH. Okay, and so so in this case it's sterics. Okay, now for this one here, right, you're going to say, okay, what we're going to do, we're going to say, we have an alkene, we have water, but we have the mercury, right? So that's going to add, what is that going to do, right? So we're going to add OH across, right? But this is going to want to be on the higher, OH on the higher side. Okay, so we're going to look at this, right? So this is 1, 2, 3. This is tertiary. This one here is secondary. So your product is going to be like this. Okay. Add OH to H. Now, if you were going to do the if we were going to do hydroboration, right, you would say, okay, well, here again, here is the alkene, right? Here's the reagent, but remember the boron, the BH3 gives the opposite product, the anti-Markovnikov product. Now, I used to tell students the way that you can remember it if you blank in the middle of the test. Notice how this one, in the second part, it uses peroxide. So the HBr peroxide, right, flips this. This one also, in this flip, is a reaction where you give the anti-Markovnikov. Now, the reason for it is different, but it is kind of, I always thought it was kind of funny that two of the big ones that switch to preference both have peroxide within their reagents. Okay, so for this one, you would end up with the opposite, with the anti-Markovnikov product, where we added the H over here and the OH here. So here's a what is it? Sort of a cheat sheet for this. So both of these are going to give the same product. However, with the acid catalyzed hydration, there's a good chance you're going to get rearrangement. Okay? And if you want to do the anti-Markovnikov product, you're going to do the hydroboration. So. Now adding HCl and ClCl are going to work very, very similarly. Okay, so we're going to add the, but in this case, instead of H and Cl, we're going to add Cl and Cl. Okay, but the mechanism is exactly the same. Okay, now the one thing is, one of the big differences for this is the fact that this ends up being an anti-addition. Okay, so one halide is going to be on a wedge, the other one is going to be on a dash. Again, not too big of a deal with the, not as big of a deal with an alkane, although it can, but certainly it's a bigger deal with a cyclic alkene. Okay? And it all has to come down to the mechanism. Okay, so if you have this, right? So remember way back when we were talking about interactions, we were going to have the London dispersion forces. Every once in a while, we're going to get this little, very tiny induced dipole. When that happens, the alkene can swoop in and push this away. Now, you're going to end up getting this intermediate when that happens. Right, now, in this case, it doesn't matter which side you put it on because they're both secondary. But you're going to get this. You can draw a resonance structure where these lone pair, right, one of these lone pairs is going to get attracted to that carbocation, and so you're going to form this resonance structure. It's what's called the bromonium ion. It's this one here. Okay, end up getting a positive charge. Now, the reason why this is important is because this bromonium ion is going to block one of the faces. Okay, so if this first bromine comes from the top side, from the top face, it's going to block the top face, right? So the bromine can't come in from the top, right? It can't, if it's going to come in here, it's going to get bunk, it's going to bunk into the bromine. Okay, so it's just a lot easier instead to come in from the bottom. Okay, and so if it comes into attack, it's going to push this way. Now, there's no preference on does it come in for 1 or it can come in to 2 and go this way. In this case, there's no preference. But the important thing is, if this top face is blocked, then the only place the bromine can go is on the bottom. Okay, and so you end up making, in this case, a pair of enantiomers. So that's why it's it's an anti-addition. Okay, it's because one of those faces is blocked. Okay, now it can make a difference on linear, regular alkenes. Okay, because whether you get a cis or a trans, okay, because it's an anti-addition, it can give slightly different products. Okay, so here it's a meso compound, and here it's a pair of enantiomers, depending on if you're adding a trans or a cis or a trans. Okay. Now, if the problem is, if you are doing this and your solvent is wet, okay, remember the the halide that gets released is generally a pretty crummy nucleophile. Okay, and so what ends up happening is the first step is the same, but instead of the halide coming back and attacking, what can happen is the water can attack. Okay, and so it's going to be very important. So you're going to come in here, normal sort of mechanism, first part. Okay. So come in here, if you're going to add bromine across a double bond, this is going to attack, you're going to form the bromonium ion, no problem. And we're going to release the Br minus. But before this can come in and attack, right, the water comes in. Okay? And so it forms the new bond. Okay? And then we just clean it up by removing the hydrogen. So be left with the H on one side and the halide on the other, and that's called a halohydrin. Okay? And it turns out, right, it's just like with the Markovnikov, right? The first one goes on, and then the more stable carbocation is formed, and that's where the second attack comes in. Okay, that's where we do our attack. That's the exact same thing is going to happen here. Okay? So, right, this is a lot more stable carbocation. So this is where the carbocation is going to be. So that's where the water attacks. So the OH goes on the more substituted side. Okay. So it's a Markovnikov type product. So if we do this, right, remember that benzene is a completely different thing than a regular alkene. Okay, this is styrene. Right? Stuff like that. This is a styrene molecule. This is what polystyrene is made out of. Okay, so we have an alkene here. Right? We can't use these because this isn't an alkene. This is a benzene, and those work differently. Okay. Aha. We have here's our reagent. Okay. So what does this do? Right? Turns a double bond. We're going to add CLs across both sides. Right? And so what we end up getting is we end up getting this. Cl, Cl. Now for this one down here, same thing. But now there's water around. Okay, and so what that is going to do is we're still going to add across the alkene, right? But what we're going to get is we're going to get Cl on one side and OH on the other. We're going to get water adding to the other. And so we need to figure out what that is. And so this is secondary, this is primary, right? Markovnikov says the first thing that goes on is on the lower, and then the second thing that gets added is on the higher. And so what we're going to do is we're going to say, okay, the Cl and then OH, right? The OH came from the water and we had released it, right? So you can think of it plus HCl. Okay, and so this can be problematic, you know, particularly in the summertime where it's hot and humid, right? Your solvents can pick up a little bit of water, so you have to be careful when doing this thing. You have to worry about the weather, or you have to be very meticulous about keeping this dry, or you're going to form a lot of this in your, in your product. Now we're going to switch gears a little bit here for some other reactions. Okay, we're still going to be adding across we are still going to be adding across alkenes, but these are a little bit more complicated reactions. Okay? And so for here, we're going to be using this. It's what are called peroxy acid. So if you have benzoyl peroxide, I think it's this, for the acne medication, stuff like that. But this one has a chlorine on it. It's a little more stable, I think. Or reactors. Anyway, it turns out that this is what's called a peroxy acid. So if there's only one, if this was just an H, it would be a carboxylic acid. But it's this, but it's adding OH to it, and so this is really unstable. And so what it does is it turns an alkene. Okay. So what we're going to do is we're going to take our alkene here. And we're going to make basically what's called an epoxide. We're going to add that right there. And so it's going to add like that right to it. leaving behind the carboxylic acid. But this is the important part, forming that peroxide. And you can use this to do a lot of different types of chemistry. This is very reactive. Okay. Now, it does add specifically. So if you think about these here, this hydrogen, the groups, it kind of comes in and clinks right on the top. So this hydrogen, well, here, let me do this in a different color. Like that. So CH3. So that ends up being this. Okay, we're going to add, say we're going to add to the top CH3, 8, H. H, like that. Now, if you were to add it from the bottom instead, you would actually make this an Hmer here. You would just go and flip it over. But notice how the things that are on one side of the alkene here, on one face of it, end up both on the wedges. Things that are on the opposite face end up on dashes. Okay, they don't mix and match. So here is the mechanism. I'm not going to keep have you memorize this, but it's the O, and that's part of the OOH. It's this O out here that ends up forming this O here. So if we're looking at this, right, so MCPBA, right? So we have an alkene. Okay. We have MCPBA, right? So what does that do? So this is our reagent, and so it takes alkene, and we're going to make the epoxide like that. So we're going to add it right here. Like that. If you wanted to put it in stereochemistry, it would be like this. Now, if we wanted to put, so we've put HOH across here. Okay, it turns out that there's a couple of different ways that you can actually do OHs on both sides, and for the and for that, the primary way is to use osmium. It's one of the few times we see osmium in here. Okay, so what it'll do is it'll take, right? So it'll take carbons of the alkene, right, and add OHs across both sides. Okay. You can also do this with cold permanganate too. It's a little more problematic, but osmium's a lot more toxic than permanganate, and so not that permanganate's something you want to drink or anything, but you can sometimes get away with it with cold permanganate. We'll talk about what happens if it's not cold in a little bit. Okay, but the OH adds across both sides. So the thing is, it is also a syn addition, and so the OHs are going to be, so the OHs that come from here are actually from the osmium. Okay, and so they come in here and click right in here, and it's called an osmate ester because this looks like an ester if the osmium was a carbon. Right, that's kind of general structure for an ester. So that gets oxidized away, or it's oxidized away, and the OHs are left where they were. Okay? And so it's a syn addition. Okay? Now the problem is, like I said, osmium is expensive. It's also very toxic, and so what we can do is, instead of using a stoichiometric amount, we can use we can recycle it inside this. And so if we are going to be oxidizing the alkene from here to here, we need that, and ultimately what's called reduces the osmium. We can oxidize it back up, but we need something to oxidize it, right? And so if we're going to oxidize the osmium back to the OSO4, we need to have something that's sacrificial, and so for here it's in methylmorpholine oxide. And so this is very cheap and easy to separate, and so we can put this in here, and it'll so that instead of using, if we had 1 mole of this, we'd need 1 mole of osmium, which would be expensive to not only purchase but also to dispose of. Okay, we can use, for every one of this, we use a tiny amount of osmium and a whole bunch of this. Okay? And so you can see here it's 0.1%. So for every kilogram of this, okay, we need 2 grams of this. Okay, or for every gram of this, we need 2 milligrams of this, and a whole bunch of this. Okay. Now, I mentioned something about oxidizing and reducing. The book goes through this into a lot of detail, okay, and assigning numbers and things like that. I'm more qualitative when it comes to this. Okay. So with the so remember back in Gen Chem when we were talking about this, we were talking about with charges. You were talking, if it went from iron 3 to iron 2, that got reduced, right? Because the charge itself got reduced. Okay. We don't really have that situation here, but we like to think about oxidation and reduction reactions. And so for an oxidation and reduction reaction, what we're looking for is increasing the number of polar covalent bonds in the with a carbon, and it's increasing the C electronegative. Okay, so that can be, typically it's going to be a CO, but can also be adding CCl or CN or CS, CF, things like that. Okay, if we're increasing, if we go from starting materials to products, if we've increased the number of those, we've said that it's been oxidized. The other way you can look at it is if the product has fewer CH bonds, okay, that means it's also been oxidized. You can think of it either way. For reduction, it's just the opposite, right? We've added CH bonds to the molecule, or we've reduced the number of C electronegative bonds. Okay? And so if you look at something like this, right, you go from a carboxylic acid, this carbon here has 3 CO bonds, okay, and no CHs. And you're like, wait, hold on, there's an H here. Yeah, that's bonded to the oxygen, it's not bonded to that carbon. Okay? But when we go over here, if we've reduced it, right, now there's 2 CO bonds. Okay, there's also an increase from 0 CHs to 1 CH. So we consider this to be a reduction. You can also look at it here, right? You take the aldehyde and you reduce it. You can reduce it further, so now there's only 1 carbon-carbon, or carbon-oxygen bond. Okay? And there's 2, and now you go from 1 CH bond to 2. Okay? The opposite is true for the oxidation, right? So here you have, right? You have 0 CO bonds, and as you go across CO, right here, 2 CO. 3 CO, right? Here, and here. If you want to look at the CH bonds, right? So here we have 3 CH bonds, right? They're all right here. This is 2 CH. Here. 1 CH. Right here. And here there aren't any CHs, right? That's an OH bond, not a CH bond. Okay, so you can see it, look at it however you want. Okay. So a nice multiple choice question would be, looking at this, going from the alcohol to the aldehyde here, is this reaction a oxidation or a reduction of that carbon? So, and you'd say, oh, we're increasing the number of CO bonds, so it must be an oxidation. So one of the things we can do with alkenes, and we can do this with the alkynes too, but we'll talk about that in the next chapter, is you can actually use these to slice. You can actually literally slice through these. And so if you have a double bond, you'll end up with carbon-oxygen double bonds. Okay? For here, for the alkynes, you could do the same thing. However, you end up with 3 CO bonds, okay? And so you end up with, but you can't really have a CO triple bond. You can, but that's carbon monoxide. You can't really do much with that. But you can make it into a carboxylic acid. Okay? So we're going to focus mostly on the alkenes here. Okay? And so what ends up happening is with ozone, and we either use dimethyl sulfide, okay, which is the really smelly stuff that you add, that they add to natural gas so you can smell it, or you add zinc and a little bit of acid. Okay? And so what ends up happening is, I'm going to put a hydrogen here, what ends up happening is you slice this here and then you make this into O's. Okay? Like that. And so if we wanted to label these carbons, 1, 2, 3, 4, 5, 6, 7. So obviously it's not going to be how you'd want to do it for naming, but that's beside the point. 1, 2, 3, 4, 5, 6, 7. Right, and there's this aldehyde here. Right, that's an H, not a 4. Okay, and so the way this works, I'm not entirely sure that they know exactly how this all works, stuff like that, but you end up getting this rearrangement, and so you form this what's called this ozonide intermediate, and then that gets cleaved, or that gets reduced, stuff like that, down to the aldehyde or the ketone. And so what ends up happening is you end up, sort of making this head-to-head. Now, this can also be done with permanganate. Now, this one is room temperature under more forcing conditions, so a little bit of heat in here. Okay, so you can also slice this and put O's here. However, aldehydes can't survive, and so if you form this, right? So there's an H here. I like drawing it like this, where the COHs are pointed towards each other, so you know exactly where that double bond was. And this is totally fine. If this was an ozone, right, we can draw it like that. But this cannot survive. Okay, so this part here can't survive. And so, because that's the aldehyde, and so it ends up getting further oxidized into the carboxylic acid. So it ends up making this. So this is your final product here. So you could either draw it like this or you draw it like this. Okay. So if we have this, right? So that's out. We have, right? So we have our aldehyde here, or alkene here. What's our reagent? Well, it's ozone. Right, so what does that do? So alkene, right? It turns it into, it cleaves it into that. And so we're going to cleave this, right? Add O's on either side. And so we're going to make, right? And there is an aldehyde here. So that. So those are our products. Now for the permanganate, right, again, we're going to be, right, we have an alkene. Right, we have permanganate. It's going to be cleaving because it's not cold. Okay, so we're going to form, right? There is an H here, so we are going to form this. However, this can't survive. And so what we're going to end up with is this OH, and then like this. So these are our products now. So here, the aldehyde survives for the ozone. For here, it does not. For here, it does not. This was originally the aldehyde, but in the presence of permanganate, it gets oxidized. And how do you get 3 CO bonds on a carbon, you make it into a carboxylic acid. Now the last part is catalytic hydrogenation. Okay, and so this one, what you're doing is you're adding HH across. Okay, so you can see this if we're going here and CH2. Right. Those don't go away, but what we're going to do is we're going to add H and then another H here. Okay, so H on one side, H on the other. And typically these are going to be done obviously with hydrogen, but you need some sort of transition metal catalyst, whether it be platinum, palladium, nickel. Those are, you know, ruthenium, some sort of really, you can get crazy ones with that. But usually it's some sort of transition metal. But you basically take a double bond down to a single bond, right, for the alkene. Now, not exactly sure. I don't think they know. Again, this is exactly how this works, but they do know that the hydrogen, when it absorbs onto the catalyst surface, it breaks apart, and so now there's individual H molecules on here. The alkene, when it comes down, it's going to grab the two hydrogens, okay, and then pull away, and those hydrogens are going to get added to the same surface or same face. Okay, so it's similar to if you take a cupcake with frosting on it and you come in and you dip it down into sprinkles. Right, those sprinkles are only going to be on one side, one face of the brownie, just on the face with the sprinkles, or with the frosting. Right? That's what's going on here. So it's a syn addition. Okay? And that's it. Good luck.